things are changing so rapidly, I can't keep up, blah, blah, blah. I want to take you back briefly to 1895 to think a little bit about this. Henri Becquerel has just figured out what X-rays are. He's discovered X-rays. And imagine you're living in this time frame. Electric and internal combustion engines are now being used to build cars. 6 years later, Marconi is going to show that he can do telegraphy without the transatlantic cable. He does it with wireless across the Atlantic. The Wright brothers, 8 years from 1895, will show heavier than air flight. And then Einstein blows up Newtonian physics with his four famous papers in 1905. So, and then lots of other things happened during that first couple of decades, first 2 or 3 decades of the 20th century. So I think that we are living in a time when there's an awful lot of stuff happening, new technology is coming along, and it's confronting us with changes. But imagine living in that time frame, we probably would have felt very much the same way. So, and if you go to the second half of the 20th century, of course, all kinds of things happen. We discover what DNA looks like, you know, the double spiral and magnetic resonance imaging comes along, and a bunch of other stuff. Are you clicking for me? Is that how that works? And this doesn't work. Okay. So now I'm going to take you back, not to 1895, but just to roughly 1969 or so. I was a graduate student at UCLA, and I was in Leonard Kleinrock's team that was doing monitoring of the performance of the then ARPANET project, which was started by the Defense Advanced Research Projects Agency. Part of its rationale was to connect different kinds of computers together at different campuses in order to help them share each other's computing and software resources, because they couldn't afford to build or buy another world-class computer every year for every research department that it was funding. So my job was to connect the Sigma 7 to the little blue packet switch. We call them interface message processors. Now, the Sigma 7 is in a museum now, and some people think I should be there with it, but I'm here. And that was the beginning of a networking effort to figure out how to make disparate computers interact with each other in a useful way. Next slide. So this is what a packet switch looked like back then. It was delivered by a company called Bolt, Beranek, and Newman to UCLA, and you'll notice that it's in an extremely heavy-duty metal encasing, and the reason is that they knew they were delivering it into an extremely hostile environment, namely a building full of graduate students. And so they wanted it to resist the usual curiosity. Let's go to the next slide. Now, in the course of the internet development, Bob Kahn, my colleague in the original design of the internet, had already started working on mobile packet radio as well as packet satellite. And why would he do that? Well, he had conceived of the possibility of using computers in command and control. And in order for that to work, the computers would be in mobile vehicles, they would be in ships at sea, and possibly aircraft. And the ARPANET that I showed you a little picture, the beginnings of, was built on dedicated circuits, telephone circuits connecting the packet switches to each other. You can't do that with ships at sea because they get all tangled up and the airplanes never make it off the tarmac and the tanks run over the wires and they break. So he had already started investing in mobile packet radio as well as packet satellite. So at SRI International in Menlo Park, the team there using the packet radios built this van that carried a complement of packet radios around the Bayshore area in order to test the ability of transmitting and receiving data in a dynamic topology of these packet radio systems. Next slide. So this is what the packet radios look like. Those white things were about a cubic foot in size. They cost about $50,000 each. All of you are carrying in your pockets or your purses something which is far more powerful than these boxes were and costs a lot less money. But that's the state of the art at the time. And I might point out that these were using some very sophisticated spread spectrum technology of the day, using surface acoustic wave devices to do the cohesion of the transmitted spread spectrum signals. Next slide. Now, just to show you that we were very advanced in our thinking, we were also interested in doing packetized voice and packetized video. This is way back in the mid-1970s. But we know that that's going to be important, voice, video, and data for command and control. So we are experimenting with packetized video and packetized voice, and you can see we used a very sophisticated telephone here to test the technology. Now, what you don't know, because I haven't said it yet, is that the ARPANET backbone speed was 50 kilobits a second, which was broadband at the time. The packet radios could run at either 100 kilobits or 400 kilobits a second. Now, some of you will remember that a typical digitized voice stream is 8,000 samples a second, 8 bits each, 64 kilobits. If you differentially encode, you could get it down to 32 kilobits. You can't cram a whole lot of 32 kilobit voice in a 50 kilobit channel or a 100 kilobit channel. So we also were investing in compression mechanisms for compressed speech, for example. One of the algorithms was called linear predictive code with 10 parameters that modeled the voice tract as if it were a stack of 9 cylinders changing their diameter as the voice is being generated, excited by a formant frequency, which you can think of as pitch. So the 10 parameters would be sent to the other side in a little array of 20 millisecond packets. They would be inverted, the algorithm would be inverted to produce sound. Now we got the data rate down to 1,800 bits a second for that kind of packetized voice. And you know, when you go from 64 kilobits a second down to 1,800 bits a second, you lose a certain amount of quality. So anyone speaking through the system sounded like a drunken Norwegian. Now, at the time we were doing this, I was already at ARPA, and I now asked to demonstrate the packet voice system to a bunch of generals in the Pentagon, and I'm trying to figure out how I'm going to do this. And then I remembered that one of the participants in the packet voice system was Ingvar Lund from the Norwegian Defense Research Establishment. So we had Ingvar speak through the Autovan system, which was the normal circuit switch voice network for the Defense Department. Then we had him talk through our packetized voice system, and it sounded exactly the same. And I didn't tell any of the generals that everybody would sound that way. Now, coming back to the packet van that I had shown you a moment ago, there's another one of my favorite stories. Some of the engineers would be driving up and down the Bayshore Freeway, and sometimes they would pull off to the side on the freeway, and whoever was driving would go into the back with the rest of the engineers, and they were trying to measure, you know, the shot noise and other interference and how many packets were being lost and what was the quality of the transmission. So the story goes that one day the van is parked on the side of Bayshore 101, and there's nobody in the cab. And the police car pulls up, and he sees this nondescript van with a stacked dipole array antenna sticking up the top. And so nobody's in the cab, so he knocks on the back door. And whoever's in there opens up the door. And now this guy sees a bunch of bearded guys with, you know, displays and oscilloscopes and other stuff. And he looks at them and he says, "Who are you?" And one guy says, "Oh, we work for the government." And the cop says, "Which government?" "But officer, we were only going 50 kilobits a second." Okay, next slide. So fast forward now to 1977. I am at ARPA, I'm running the program, and I'm eager to demonstrate that the TCP/IP protocols that Bob Kahn and I initiated and many other people contributed to actually work and can be made to link very, very different networks together. The packet satellite system over the Atlantic, linking the western part of Europe to the eastern part of the US, the mobile packet radio system in the Bay Area, and the ARPANET, which by that time had been extended into Norway and the UK through an internal synchronous satellite hop. So on this date, November 22nd, I had the Bayshore Freeway guys pumping packets through a gateway into the ARPANET, went all the way into Europe, went down to University College London, hopped out into the packet satellite system, went through another gateway, back into the ARPANET again, and then all the way across the country down to Los Angeles to USC Information Sciences Institute. And you know, you all know that San Francisco and Los Angeles are about 400 miles apart, but the packets went 88,000 miles because they went up and down through 2 synchronous satellite hops back and forth across the Atlantic in the United States. And it worked. And I remember leaping around in my Washington office saying, "It works," you know, as if it couldn't possibly have worked. It's software. It's a miracle when any software works. So this was an important milestone from my point of view because we showed that this TCP/IP thing could actually bind together very, very different kinds of networks, all of which happen to be packet switched. Next slide. Well, the idea caught on, and after ARPA had spent money to build the ARPANET backbone running the packet radio and packet satellite nets using TCP/IP, starting on January 1, 1983, which is sort of the operational birth date of the ARPANET, other agencies in the US government decided that they were going to get involved as well. So the National Science Foundation, Department of Energy, and NASA all built backbone networks. NASA and DOE to link its laboratories together. And there was controversy over whether to use the TCP/IP protocols or the Open Systems Interconnection protocols. That controversy went on for quite a while, but TCP/IP got implemented more quickly and more broadly than the others. The NSF wanted to connect some 3,000 research universities to the 5 supercomputers that it was funding with the Department of Energy, and they chose to use TCP/IP as well for the NSFNet backbone, which, by the way, the development of which was managed by Merit, which is an organization here in Michigan. The university is part of that. MCI and IBM contributed, and IBM contributed the packet switches for the NSFNet backbone, and MCI provided the optical fiber networks. So this was an incredibly important period of time when 4 backbone networks were all being operated and interconnected together. There were limitations, however. Only people who had government contracts for those agencies, plus the military, were allowed to use the backbone networks at all. So there was no commercial traffic allowed, no private networking or anything. I'm not sure what's on the next slide, but let's go to that one for a second. That's probably, yeah, that's what the internet looks like now. I'm cheating. If you can read the tiny print, this was actually produced around 1999, but it's such a nice picture, I'm using it again. The idea behind this picture is that the different colors indicate that there are thousands of different networks that make up the internet. And every one of those networks is operated independently of the others. And they have different business models, nonprofit, for-profit, government run. They choose their own hardware, they choose their own software, they choose who to connect to and on whatever terms and conditions they can work out. The fact is that it works despite so many different independent operations because they've all adopted the same protocols. And those protocols, of course, are what make the internet functional. So this very, very distributed environment with a lot of independence associated with it is one of the reasons the internet has been able to expand now to cover some 2/3 of the world's population. The important part about all this is that the system was designed to be expandable, not only in terms of absolute scale, the number of devices, number of networks, number of termination points and the like, but also to be expandable functionally speaking. So we use layered architectures to allow these systems to be grown in functionality. So, for example, in the early 1980s, optical fiber networks were becoming feasible. And so when they were added, it was no big deal to put the internet protocol on top of an optical fiber bearing system, as opposed to a piece of Ethernet or a coaxial cable or a dedicated phone line. And as you work your way up the layers, if you don't like what you see in that layer, you're allowed to add another protocol at that layer. And some people were even allowed to add layers of their own. So when Tim Berners-Lee released the World Wide Web in 1991, he added the hypertext transport protocol on top of TCP/IP, and it just sat there and it worked because TCP allowed for reliable transfer end-to-end, and that's what HTTP needed. So this flexibility remains today. There's an Internet Engineering Task Force which adds protocols to the internet over time. There are probably 100 or more that make up the ensemble of things that you can do with the internet. Let's go to the next slide. So I think a question that all of us are asking now as we ride on the back of technology is, where is it taking us? And it's pretty obvious. Computers are everywhere. We have them in our pockets. Internet of Things is all over the place. Sensor systems are available. Systems for protecting security. All kinds of devices are now equipped to be networked in the internet environment. And the result of that is that data is also everywhere. It's being accumulated. It's being distributed. and is being analyzed and evaluated. And of course, the internet and the World Wide Web are two examples of that. There are literally millions of apps. I'm sure none of us use all million of them, but you have a lot to choose from, and especially on mobiles. And that has been another major element in the, I would say, the increasing complexity of life as we live it today. Now, of course, there are something like 5 or 6 billion users of the internet around the world, and more are coming, partly because we have more access. For example, Starlink makes the internet accessible in places that would be quite difficult to get to otherwise. And Waymo, one of our sister companies at Google, is offering self-driving car service in several cities around the United States. I don't know if any of you have ever been in a self-driving car, but I remember the first time I left my fingerprints in the back seat, because the thing took off and there was nobody in the steering wheel was moving. And to be honest about it, I got relaxed fairly quickly because there was a big display showing me what the Waymo system was seeing. And as long as it was seeing what I was seeing, I felt more comfortable that, that there wasn't some surprise on its way. But that's turning out to be a successful business. So the point here is that when technology works, it can be tremendously enabling. And I think all of us have experienced that. Let's go to the next slide. Here's another important example, assistive technologies to help people get access to computer-based systems. I'm going to pick on my wife, who is not with me today. She was off visiting art museums and things. But she was born with normal hearing. But when she was 3 years old, she had spinal meningitis, and it destroyed the ciliary hairs inside the cochlea, which rendered her deaf. So for 50 years, she had to lip read. So she went through life, went through school, raised 2 sons, our family, lip reading only. And then on the internet, she discovered cochlear implants. And so she consulted with Johns Hopkins University, and they said, why don't you come up and we'll test to see whether or not your cochlea is still capable of generating neural signals. And she was a candidate for a cochlear implant. So she went up there to get an implant. It took 45 minutes. It's an outpatient operation. She came home, waited a couple of weeks till everything healed. Then she went back up to be activated, which sounds kind of religious, but actually it was just turning on the speech processor and putting a map in it that said, take these audio signals that have been Fourier transformed into which frequencies are present and in which amplitude. I love it when I have audiences actually understand what that means. And then it stimulates one of the 16 different electrodes that are embedded in the cochlea, which is what the implant is all about. And then the brain thinks it's hearing sound. And so within about 20 minutes of having been activated, she picked up the phone and called me, and we had a phone conversation for the first time in 30 years of marriage. It wasn't a deep conversation, but it was moving anyway. And then she got home, and I discovered I had a 53-year-old teenager at home. I couldn't get her off the phone. Now, I know that's not today's teenagers. That's the teenagers that I remembered. The teenagers of today are too busy texting. But she was very eager to get every possible sound. No decibel will go undetected. So first thing she did was to call the library to get recorded books for the blind, because she wanted to hear words that she hadn't heard. So remember, she's on the phone. She calls the library and says, hello, I'd like to subscribe to recorded books for the blind. Oh, no problem. Name, address, phone number. Now, you're blind, aren't you? And she says, no, I'm deaf. And there's this, and there's this long pause while they're trying to figure out how's that going to work. She ended up listening to about 500 books, recorded books. Then she got a little patch cord with a microphone on it. So if she's walking around or maybe having dinner, she can pin the microphone to the lapel and get better quality sound. She has an FM transceiver. So if she were here, I would be wearing a little FM transmitter with a microphone, and she would be picking that up 150 feet away. She also got a patch cord that you can plug in to watch the movie on the plane, and the only sound she's getting is from the patch cord and the movie, and not the screaming kid that's 2 seats away, because the acoustics are all gone. It's just all on the patch cord. So just to give you a sense for how incredibly powerful these technologies are, there are lots of others. I've listed some here, and I'm not going to go through all of them. But I want to emphasize that one of the promises of the kind of technology that you and I are interested in offer an incredible ability to enhance people's capacity to deal with computers and computer-based systems. Screen readers as an example. I think we're crossing into a new territory, and I'll come back to AI a bit later, but with artificial intelligence and large language models and the kind of natural language interfaces that we have, we're crossing into a very new kind of territory where assistive technology is quite different from trying to get something to read a web page and try to help you figure out what's on the web page by getting a serial rendition of it. The kind of interactions that we have with large language models are natural language exchanges. And that is even more enabling in many ways because it's a very common kind of way of interacting with people. Now we can interact with these artificial intelligences and computer-based systems more easily. So there are all kinds of other medical mechanisms. At some point, optical implants may be feasible. Today, they're probably 20 years from being achievable in the same way that the cochlear implants have. And spinal implants may be even further away, although there have been some demonstrations of the recovery of limb use that has been caused by a spinal injury by literally routing the signals around the place that's been damaged in the spinal cord. So we're very excited about those kinds of technologies, and perhaps some of you are going to spend time helping to develop them further. Next slide. Well, okay, so none of these things happen without some unexpected consequences. What I tell all of my engineers is the first job, whenever you're going to design anything new, is to answer the question, what could possibly go wrong? And that's a really important question to ask and answer. Now, what has happened in the internet space, these are unexpected consequences of internet, is first of all, by enabling everyone to share what they want to share, whatever that turns out to be, we've unleashed a huge amount of access to knowledge. In the early days of the World Wide Web, people just put up web pages to share what they knew, just because it was satisfying to know that what you knew was useful to someone else. Well, frankly, as the internet has spread, there are a lot of people out there who want to share stuff that we would just as soon not see or hear. And that's a problem, because some of the content is harmful and toxic, and we're going to have to deal with that. So from my point of view, that was not an expected problem. We didn't really appreciate how harmful some people's behavior can be. I sometimes think the internet would be great if there were no people on it, but that's not in the cards. We've expanded access, which has simply enabled more and more people to get to the network. And the social media have shown themselves to have both beneficial and not so beneficial properties. Some of the algorithms for deciding what to show you next can take you down, the dark rabbit hole. On the other hand, just thinking about YouTube for a minute, I don't know how many of you have encountered this situation where you don't know how to do something. And so you go to the YouTube and you say, how do I do X for some value of X? And 17 videos are there that, that tell you how to do X. I remember one weekend, my wife and I wanted to make Chinese eggplant, and we didn't have any idea how to do that. So I said, how do you make Chinese eggplant? We got a bunch of videos, and I discovered that the Chinese eggplant is not that big, fat, black thing that I thought it was. It's this long, skinny, gray thing. And then there were all kinds of other spices that had to be added. We produced what I guess is a credible eggplant. But the point I want to make is that we have opened up an opportunity for what's called just-in-time learning. And I don't know about you, but there's a big difference between I got to figure out how to do this now, and I learned how to do it right there. It sticks a little better than I wonder why I'm learning this now, and will I ever need it? And I'm sure a lot of kids are looking at textbooks and classes and wondering, am I ever going to need what this professor is trying to teach me? So just-in-time learning has a self-reinforcing character to it, which is pretty good. We've also discovered that scaling is a big challenge. Just to take the YouTube example, there are 500 hours of video uploaded to YouTube per minute. Let me repeat that, 500 hours of video per minute uploaded into YouTube. It's not possible for us to scrutinize that using people. So the best we can do is to use artificial intelligence tools to try to detect stuff that shouldn't be there. We won't get that right every time. And there will be some things get through that shouldn't, some things that should not be blocked are blocked. It's not perfect, but handling scale is a gigantic challenge in many different dimensions in this internet environment. Unfortunately, these same tools that are allowing people to do things that they could not do before, like write things in multiple different languages by translating them automatically, it also allows people with misinformation and disinformation to generate and distribute that as well. And that's a huge challenge as well to deal with. Another unexpected consequence of the internet is the monetization of some of its elements. When we started this program, we gave away the internet addresses to people who needed them as part of the experiment. And as it became a commercialized activity, you could get your allocations from the regional internet registries. You had to pay a kind of annual fee to stay registered and make sure that address block was assigned to you. Domain names, the same thing. We used to give them away for free. And then around 1992, the National Science Foundation said, wait a minute, we're spending research dollars funding an organization to allocate and maintain domain names. Why don't people just pay for them? So domain names became a monetized element. Now I have to embarrass myself. Professor Chen mentioned that we had lunch before. I had to admit to the students over lunch that I had done something particularly stupid. When I was at ARPA and funding the program, I could have allocated to myself a /8 of IP addresses. That's 16 million addresses. And I didn't do that. But a good friend of mine did, a guy named, I'm sorry, I just drew a blank, Jun Marai, at Wide at the University of Keio University. Now, he was allocated this for a nonprofit research program, and it was absolutely all up and up. And then more recently, I would say in the last several years, he sold that 16 million block of addresses for $400 million. And it went to a nonprofit, and it's going for good purposes, and it makes 20 million a year, and it's all wonderful. I was just sitting there when I heard that, and why didn't I allocate myself a /8 while I was the program manager, duh. So one other thing I have to say about the internet, when Bob and I were doing the original design, remember we thought we were doing this for the Defense Department as the underlying system for command and control, the communication system. And so we did not want to do what the telephone system did, which was to have country codes. Because we thought, if we had country codes in this design, suppose you were going to invade country X in 2 weeks, would you have to go to country X and say, listen, we're planning to invade you in a couple of weeks. Can we get some IP address space from you so we can run our command and control system while we're invading you? And I thought, that isn't going to work. So we made this a topological allocation of address space and not a geopolitical one. Where did I want to go? Oh, okay. So the internet is insensitive to its traffic crossing borders. And what that means is that harm can happen across international boundaries. That means if we're going to fight crime, we're going to have to cooperate with other countries in order to hold parties accountable in one jurisdiction, harming people who are in a different jurisdiction. And there is a lot of work going on internationally. There's a cybercrime treaty, which was just agreed recently, and there was a preceding one of the Budapest conventions that are about a decade or so old. So more international agreement is going to be needed in order to fight harmful behaviors in the online environment in an international setting. Now, one thing that some of you will have heard about a problem that showed up with a particular service called CrowdStrike. And in that particular case, an update was sent, and the update caused every computer that was using the CrowdStrike security system to exhibit the blue screen of death. And if you rebooted, it did the same thing. It required physical rebooting of the systems to fix that, and it propagated across an enormous number of different applications across the internet. This is simply a lesson that says when you become very, very dependent on something, you should be thinking hard about how to make it resilient. And I would argue that our resilience in this space is still lacking. I would challenge you, for example, to try to go through the day without your mobile. And I would guess that for the most part, you would find it frustrating, if not impossible. Here's a scenario that is made up, but it's an example of what could happen. Suppose that you're using two-factor authentication on your mobile. So you try to log into your email, but your mobile isn't working. The battery is dead, you're not getting a signal. So you can't get to the email. The trouble is that that email that you were waiting for is the one transaction that will save your company so your company goes bankrupt. All because the mobile wasn't available. You remember the poem, "For want of a nail, blah, blah, blah." So I worry a lot about resilience in this environment where we become increasingly dependent on particular technologies in particular forms, and the engineers, that would be a lot of us, haven't paid enough attention to the resilience of the system and backup and other kinds of alternatives. Next slide. So I've just pointed out single points of failure. Finding mechanisms for discovering single points of failure would be a very important thing to do. Maybe some of the artificial intelligence mechanisms could help us with that. Supply chain risks, we saw that during the pandemic. We discovered that supply chains fragmented because certain kinds of production couldn't be done because people couldn't be co-located with each other because of the COVID virus. And the cascade failures I've already mentioned, the one at CrowdStrike. Colonial Pipeline was another example. It was a ransomware attack. They shut down the pipeline operation because they couldn't keep track of the transactions. And the result was a cascade failure across the eastern part of the United States where gasoline became less and less available. What about the situation where people bring their own devices into what should be a controlled environment? At Google, we allow our employees to bring their own laptops and mobiles, but we don't allow those to get connected to our network. And there is extra software added to what we issue to our employees to prevent that from happening, or to prevent them from downloading software that might have come from who knows where, with what purpose. So there's a whole lot of extra work that goes on in trying to protect not only the cloud environment, but also the devices that get access to it. Next slide. So I want to take you back again in history to Xerox Palo Alto Research Center back in the 1972 timeframe. Imagine what they were living in at that time. I want you to, if you don't know, let me just remind you. In that early 70s period, they had Ethernet, which was running at 3 megabits a second, which was really, really fast compared to everything else, certainly compared to a dial-up modem. They had a laser printer. They had multi-font bitmap graphics. They had a Windows-based computer that was called the Alto machine. They cost $50,000 each at the time, and every single employee at Park had one. Those guys were living in 1992 in 1972. And what did they do? They recognized that they were entering into a really different period. And so they hired anthropologists and sociologists and psychologists to observe the behavior of the people living in and using that environment. And with in the intent of trying to understand how technology would impact their behavior. I sometimes wish that a lot of the big tech companies of today had done the same thing, including my own, to try to understand how these technologies affect people in such a direct way. So we've already talked a lot about information and misinformation and disinformation, but I wanted to mention an organization that's recently been set up. Many of you have heard of the International Committee on Climate Change, or International Panel on Climate Change, IPCC. Well, there's a new one called IPIE for the International Panel on the Information Environment. And that panel, which is made up of about 3,000 scientists, are trying to understand and observe how misinformation, disinformation, malware, and all these other things propagate through the internet, and how to recognize and defend against that. And so yet again, climate change is a huge threat, so is information pollution. And some of us, maybe not you, but I certainly feel some responsibility for trying to deal with that problem. I also have a genetic theory of why misinformation seems to propagate so quickly through the system. Thomas Edison, oh no, it was the guy that wrote Tom Sawyer. Yeah, yes, thank you. He said that the falsehood runs around the earth 3 times before the truth puts its shoes on. And I remember thinking, well, that was an interesting observation. Do I have any understanding of why that's the case? And I finally realized it's genetic. And so imagine, it's 50,000 years ago, and you're a Neanderthal or Cro-Magnon, and you see a bear. Now, a couple of things could happen. You could be one of these contemplative Cro-Magnons thinking, gee, I wonder what kind of bear that is and how many family members it has. And you don't survive to contribute to the gene pool. The other one says, it's a bear, run. And they survived in the gene pool. So we have genetically understood that warnings are important to our survival. Most of the misinformation and disinformation that I see involves warnings about something. Some bad thing is going to happen, some bad person is going to hurt you, some bad company, whatever it is, they're all warnings. And people resonate with the warnings because we've genetically learned that warnings are important to survival. And so that's my genetic theory, which is unproven, about why we respond so assiduously to the warnings that we see. So this has led me to believe that 2 important desiderata in the internet environment, one of which is accountability. For a long time, I was a big fan of anonymity, and I believed that it was important that you should use the internet without having to log into it or be known. I still think that's important. I don't think you have to be known to do a Google search or something. However, I do feel that some accountability is needed, more accountability is needed. And so we should be able to pierce the veil of anonymity at need and under the right circumstances. A kind of a weak analogy of this is license plates, which are mostly just random strings of letters and numbers, except my plate, which is Surf's Up. I could not resist that. So it's pretty obvious who's driving that car. But for the most part, some people are given the ability to look up the random license plate to figure out who owns the car. That may not be who's driving the car, but it's the beginning of trying to reveal information that might be needed. So I think that we are going to have to pay a lot more attention to accountability. At the same time, we need to give people and organizations and even countries more facility for protecting themselves, more agency. So we need more tools for protecting people's privacy and their safety and security, which has led me to think about the possibility of an internet driver's license. Just think for a minute that we don't let the teenagers have the keys to the car until they've demonstrated that they know the rules of the road and they've shown that they can drive the car safely. I don't really believe we should have an internet driver's license that you can't use the net without it, but teaching people the risk factors and how to use the network in a safe way actually would be a useful thing. So I think a kind of internet driver's license would be a good idea. Next slide. Okay, I want to be concerned about time here. Are we still okay? Yeah, okay. So this is the obligatory artificial intelligence slide. I mean, you can't give a speech these days, especially not coming from Google, without it. So some of you will remember that there were 3 big phases in AI. One of them was called heuristic programming. And at Stanford, I remember working with several of the people there, including McCarthy and Ed Feigenbaum and others, on the use of these heuristic programs. All that meant was that it didn't always work. If it worked all the time, that was engineering. Otherwise, it was AI. But that didn't scale very well. So then came expert systems in the 1980s where you try to extract intelligence and knowledge out of somebody's head by creating if-then-else clauses. If this symptom is present, then there's a 30% probability that your patient has that disease and you should apply this particular remedy. And as you drew the knowledge out of somebody's head, you created increasingly large clouds of if-then-else clauses, which eventually started conflicting with each other. And so that didn't scale very well either. And then came the multi-layer neural networks, which had been speculated about earlier on, but some of you may remember a book that was by Minsky and Papert that talked about perceptrons, which is a 1-layer deep neural network. And it didn't do very much. And the whole book was all about a 1-layer neural network doesn't do very much. If they had just looked at even 2 layers, they might have discovered that it can do a lot more than they thought. So there was a kind of nuclear winter for a while with regard to neural networks. But as every one of you knows now, the ability to build multi-layer networks of hundreds of layers deep is now physically possible thanks to special purpose hardware and new kinds of software structures. And they have shown remarkable promise in being able to do things that most of us can't do ourselves. For example, translating 200 languages into 200 other languages, or writing a poem in Elizabethan haiku, or writing a piece of software. Now, I've experimented with some of these things, and you have seen, the ChatGPT stuff and the AlphaGo stuff from Google, and now the more recent Gemini series. All of these are astonishingly capable of doing things that are unexpected and surprising. I tried doing a few things. Now, entertaining stuff seems perfectly okay. Write me a haiku, write me a play. At one point, I asked one of the bots to write an obituary for me. And I thought it was a reasonable test because having ingested a lot of stuff from the web, these systems would have seen obituaries and they'd understand what the format is. And there's some stuff about me in the Wikipedia and so on. So I figured it was a reasonable guess. And I said, please write a 700-word obituary for Vinton Cerf. And it did, it starts out, we're sorry to report Dr. Cerf passed away. And then it gave a date, which I thought was way too soon. I'm not happy about that. And then it got to my career, and it conflated stuff I did with stuff other people did. I got credit for things I didn't do, and it gave credit to other people for the stuff I did. And then it got to the family members part, and it made up family members that, as far as I know, I don't have. And so, look, I'm not an expert in any of this, but I remember thinking, I wonder why it did that. And it occurred to me, and remember, this is my little cartoon model of understanding this stuff. I'm no expert. But I'm thinking, well, I wonder if context plays a role here. Imagine that Whit and I would naturally end up having our biographies on the same webpage. We're both Turing Award winners. We go to the Heidelberg Laureate Forum. It's a very good probability that a webpage would have both of our bios on it. But the thing which is absorbing text and using it to train the multi-layer algorithm doesn't know that this paragraph is about Whit and that paragraph is about Vint, because it's not laid out that way. Where there are no signals in the HTML that tell you that. And so you could easily imagine the probability of the probability weights that are in the neural network could easily pluck things out of his bio and out of my bio and put them together in a perfectly good sentence. So my guess is that we still have some work to do to deal with contextual kinds of things, among many others, to make these things work well. But that's just amusing. Now, what about the possibility of using these things for really serious, high-consequence applications like medical diagnosis, medical treatment, financial advice, maybe marital advice? I mean, you have to worry that the high-risk stuff could lead to some really serious consequences. So I think companies that are offering AI-based products and services should show evidence that they have taken into account the high-risk factors, if there are any, and should be able to demonstrate that they have taken steps to mitigate those risks to reduce the potential harm to a user. I've already talked about hallucinations. I talked about my obituary. Automatic programming. Now this I had trouble believing, but maybe many of you have tried using some of the smart bots to do some programming. I was really very surprised. I asked one of the bots to write a program. I said, let's calculate how many atoms there are in the universe. And so I said, please write a program to do that. And it did. And it walked through the rationale for the assumptions that it was making, because it had to make a whole bunch of assumptions, like how big is the universe and what's the density and mumble mumble. And it got all done, and it said, it wrote a little program, and then I said, run the program, and it did, and it got an answer. It was something on the order of 10 to the 88th atoms in the universe. Of course, I don't have any way of checking that, so yeah, I don't know. I do have to admit, though, that I did do something stupid once. Some of you will remember that the original internet design had a 32-bit address space for IP version 4. And we discovered in 92 that we were going to run out. So we developed IPv6, which has 128 bits of address space. That's 3.4 times 10 to the 38th addresses. And I used to say, well, that's enough addresses so every electron in the universe can have its own web page. And then somebody from Caltech sent a note, dear Dr. Cerf, you jerk, there are 10 to the 88th electrons in the universe and you're off by 50 orders of magnitude. I don't say that anymore. Every one of you has probably used real-time language translation or at least transcription. I know I certainly do for a lot of the conferencing tools that we use these days. Having a transcription for somebody who's hearing impaired like I am is hugely helpful. And the fact that you can do that now reliably is pretty astonishing. Let's go to the next slide. So I'm going to shift gears, and this is a very brief part of my presentation. I just want you to appreciate what's possible today was science fiction a few decades ago. So next slide. So around 1976, about the time that I'm going to Washington to do the internet stuff, the US lands two landers. They weren't rovers, they were just landers on Mars, Viking 1 and Viking 2. Spectacular accomplishment. And then for 20 years, nothing worked. You know, we missed the planet, we burned up in the atmosphere, we hit the ground. Then in 1997, the Jet Propulsion Lab succeeded in landing a little rover on the surface of Mars. It was the Pathfinder project with the Sojourner little robot. I was so excited about that I got together with the JPL team that was handling communications for that mission. And we were completing each other's sentences, you know, in the first 30 seconds of our meeting. And then we said, what should we be doing in 1998 that we're going to need 25 years later? We decided we should be thinking about how to design and build an interplanetary backbone network to support manned and robotic space exploration. Next slide. Well, in fact, that's exactly what we started to do. We had prototype software running in 2004, just terrestrially. I love being able to say that, terrestrially, as opposed to extraterrestrially. I've always wanted a badge from JPL that says resident alien, but I've never been able to get them to do that. So by 2004, in January, we land two rovers, Spirit and Opportunity. They were supposed to communicate back to Earth from transmitters on the rovers directly to what's called the Deep Space Network. These are 3 70-meter dishes that are roughly 120 degrees apart at Goldstone, California, Madrid, Spain, and Canberra, Australia. The radios on the rovers start to overheat. And of course, the engineers say, back off on the duty cycle. Now, the data rate they were expecting to get was 28.4 kilobits a second. The scientists were already kind of not too happy about that. And when we said, got to back off on the duty cycle, they were even more grumpy. Until one of the engineers at JPL said, oh, there's an X-band radio on the rover, and we had sent 2 orbiters to map the surface of the planet to figure out where the rover should go, and they're still operational. So, our little interplanetary network team says, well, we have some prototype software. We could upload that. And they said, okay. So we upload the prototype software to the rovers and the orbiters. I mean, think about this, they're 200 million miles away. I mean, this is just amazing. The idea is that the rover will hold on to the data it got until an orbiter comes overhead. We'll squirt the data up there, it holds onto it, stores it there, and then it waits till it gets to the right place, and then it transmits the data back to the deep space net. Store and forward, that's packet switching. And the other cool thing is that the orbiters are not very far away from the surface of Mars. So we get 128 kilobits a second instead of 28.4. And because the orbiters are outside of the atmosphere, as thin as it is, and they have a bigger antenna and bigger solar power, they can transmit at 128 kilobits back to the deep space net. So for the last X number of years, since 2004, every rover that's gone to Mars on the American missions has used this store and forward prototype system to communicate. Next slide. So all of this is just a list of all the various systems that have landed on Mars that have been using this technology. Next slide. So this is what we think is going to be like. This is just a notional slide, but every one of the missions that's on that slide is either planned or already in operation. They are all going to need communications capability, and we're very excited about having matured the interplanetary protocols. So since those prototype times in 2004, we have been on the International Space Station running regular day-to-day stuff. We even had an astronaut controlling a little robot in Germany in real time because the latency is very low relative from the space station down to Earth and back. We've tested these protocols at 600 megabits a second from Earth to an orbiter around the moon. We've tested the protocols at 81 light seconds distance using the Dynet spacecraft that had visited 2 comets and which we were loaned by NASA to upload our software to test it. We've standardized the protocols both in the Internet Engineering Task Force and the Consultative Committee on Space Data Systems, which is made up of all the spacefaring nations. At this point, we are ready to go on the Artemis missions and the Gateway missions to provide backbone communications capability to the Moon mission. And we're trying to use that mission as a way of exercising the standardized protocols to show that they can work all the way out to Mars, which of course is the next major target. So all of us are pretty excited about the possibilities of interplanetary communication. I just met with a collection of diplomats in Washington on this topic, and the reason that I brought it up is that we now anticipate another problem. I don't know if it's on the next slide or not. Yes, okay. So you can see what's happened just in the last few years between SpaceX getting regular launches, I mean, at a rate which was just unsustainable before. And many of you are probably too young to remember Flash Gordon on TV in the 1950s, but the spacecraft always landed on its tail. I worked on the F1 engines for the Saturn rocket, and we didn't, not only did we not intend to land anything on its tail, but we threw away the first stage, which Musk quite correctly says that's like flying from New York to Los Angeles and throwing the 747 away. So I was super impressed by seeing these rockets being reusable in the first stage. But what NASA has done is triggered yet another significant sea change, because it's basically saying to the commercial sector, if you want to build habitats and build rovers or offer communication service, we'll buy that service from you. So we're now seeing commercialization happening that didn't happen before. One of the things that NASA has said is that if you build a mine on the moon, we'll buy the output. Now imagine you're the CEO of a company that's going to go operate a mine on the moon. A natural first question you might ask is, am I allowed to own the property that the mine is on? And you would be referred to the 1967 Outer Space Treaty, which says no. And you sort of think about that, and then you say, well, can I register it somehow? Well, this question, where would you register your mine? In which jurisdiction do you register it? What if somebody interferes with the operation? Where do you go to adjudicate a dispute? And even worse, what if they interfere with the operation? Who do you call? The Space Force? I mean, you know, it's not clear. So we are entering a period now in space exploration where commercialization is causing us to have to think through these questions, not 10 or 20 years from now, but 2 or 3 years from now. These will be real issues that we have to confront. Our hope is that our contribution, standardized protocols, will allow an interplanetary backbone to operate similar to the internet today with multiple providers all interworking with each other and collaborating to provide the service. But we still have to deal with a lot of these policy questions. We may need new institutions in order to address them. So I think that's the last slide. We're very close. Yeah, you ain't seen nothing yet. That's my final message, is that in spite of all the agony that we're experiencing right now, and you know, I won't go into any details, but everybody here in the academic world is aware of it. In spite of all that, I'm hoping that technology will take us into the rest of this century with some pretty exciting outcomes. So I'll stop there, and I will thank you all for your attention, and I'm happy to try to answer questions.